We are going to study Science and Technology part first. But before that, do subscribe my channel and click the bell icon for notification. Chapter 4, Effects of Electric Current. Magnetic field produced by current through a circular loop of conducting wire. We learned about magnetic lines of force of magnetic field produced by a current flowing through a straight conductor. So what will happen to the magnetic lines of force of the field produced by a current flowing through a loop made by bending the straight wire? Take a look at figure 4.8. A circuit is completed by connecting various components as shown in the figure. If the current passes through the loop, magnetic lines of force are produced at each point on the loop. As we go away from the wire, the concentric circles representing the magnetic lines of force will become bigger and bigger. As we go towards the center of the loop, the circle becomes so big that its arc can be shown by a straight line. As in figure 4.8, magnetic lines of force are shown near the point P and Q only. However, they will be created near each point on the loop. Likewise, each point will produce magnetic field at the center of the loop. By making use of the right hand thumb rule, check that every point on the loop contributes the magnetic lines of force at the center of the loop, and these lines of force at the center of the loop are in same direction. The intensity of magnetic field at any point produced by current flowing through a wire is dependent on the current, as we had seen in the experiment that we performed in last video, where a large amount of current was passed through a thick copper wire and the needle was kept near the wire. We had seen that when the current flows through the wire, a deflection is observed by the change in direction of the needle, which showed us that the magnetic field at any point depends on the current. This means that if there are n turns in the loop, the magnetic field n times of that produced by a single loop will be created. Magnetic field due to current in a solenoid. When a copper wire with a resistive coating is wound in the chain of loops like a spring, it is called as solenoid, as in figure 4.9. Figure 4.9 shows us that whenever a current passes through a solenoid, magnetic lines of force are produced in a pattern. You are aware of magnetic lines of force of a bar magnet. The properties of magnetic field of a solenoid are very similar to the magnetic field produced by a bar magnet. One of the open ends of solenoid acts as magnetic north pole and the other acts as magnetic south pole. The magnetic lines of force inside the solenoid are parallel to each other. What does this mean? This means that within the solenoid, the intensity of the magnetic field is uniform everywhere. That is, the magnetic field in a solenoid is uniformly distributed. Force acting on current carrying conductor in magnetic field. To understand how does the force acts on the electric conductor in magnetic field, let us perform an activity. Using materials like flexible copper wire, stand, electric cell, a horseshoe magnet with strong magnetic field. Procedure. Arrange the setup as shown in figure 4.10. Using the stand, fix the copper wire so that it passes through the poles of the horseshoe magnet. Connect the circuit as well. What do you observe? Well, whenever a current is not flowing through the wire, it remains straight, as in position A. When the current flows from top to bottom, the wire bends and comes into position C. If the current direction is reversed, that is, its flow changes from bottom to the top end, the wire bends but comes in the position B. This means that the direction of the force on the wire is perpendicular to both the magnetic field and the direction of the current. We know the direction of magnetic field is from north to south. In this experiment, it is noted that whenever current flows through a conductor in presence of magnetic field, a force is exerted on the conductor. If the direction of the current is reversed, the direction of the force also gets reversed. If the magnet is kept reversed, that is, its south pole is brought at the position of its north pole and its north pole brought to the position of its south pole, what will happen? Well, the experiment clearly shows that force is exerted on the current carrying conductor, and it is seen that the direction of the force depends on both the direction of current and the direction of magnetic field. Fleming's left hand rule. In the before experiment, we consider the direction of electric current and the direction of the magnetic field and found that the direction of the force exerted is perpendicular to the both. There is a simple rule relating to these directions. This rule is called as Fleming's left hand rule. Take a look at figure 4.11 and stretch your thumb, index finger and middle finger of your left hand to understand this rule. So, according to this rule, the left hand thumb, index finger and the middle finger are stretched so as to be perpendicular to each other. If the index finger is in the direction of the magnetic field and the middle finger points in the direction of the current, then the direction of the thumb is the direction of the force on the conductor. Thus, Fleming's left hand rule shows us that the direction of the current, magnetic field and that of the force on the conductor are perpendicular to each other. Electric motor. You know various forms of energy. You also know that energy can change its form. A device changing electrical energy into mechanical energy is known as electric motor. Around us in our day-to-day life, an electric motor is a boon. It is used in fans, refrigerators, mixers, washing machine, computers, pumps, etc. But how does this motor work? Figure 4.13 shows us connections present in the electric motor. Electric motor consists of an rectangular loop of copper wire having resistive coating as shown in the figure. It is placed between the north pole and south pole of a magnet, such as a horseshoe magnet, in which it is placed in such a way that its branches AB and CD are perpendicular to the direction of the magnetic field. The two ends of the loop are connected to the two halves X and Y of the split ring. The two halves of the ring have resistive coating on their inner surfaces and are tightly fitted on the axle. The two halves of the split ring X and Y having their outer conducting surface in contact with the two stationary carbon brushes E and F respectively. Now let us understand the working of electric motor. When the circuit is completed, as shown in figure, the current flows in the branch AB of the loop from A to B through the carbon brushes E and F. Since the direction of magnetic field is from north pole to south pole, so according to Fleming's left hand rule, a force is exerted on the branch AB and pushes it down. The current in the CD branch is in the opposite direction to that in the AB branch, and therefore a force is exerted on branch CD in upward direction. Thus, the loop and the axle start rotating in anti-clockwise direction. After half rotation, the two halves of the split ring X and Y comes in contact with carbon brushes F and E respectively, and the current in a loop starts flowing in the direction DCBA. Therefore, a force is exerted on the branch DC in downward direction and on branch BA in upward direction. And the loop continues to rotate in the clockwise direction. Thus, the current in the loop is reversed after each half rotation, and the loop and the axle continue to rotate in anti-clockwise direction. Thus, electric motor performs half cycle, that is, after every half rotation of the loop, the current in the loop is reversed. Commercial motors run on the same principle, but practical changes are made in their construction. You will learn about that later. Here are few practice questions given. Do answer these questions. If you have any doubt regarding this chapter, do ask in the comment section below. Do like and share the video. Thank you.